Good morning, ITS538, 16-week format. Week four, um, going over chapter five, skipping a chapter this week. And we get a little closer to reality, but something to keep in mind during these chapters is that these concepts were developed uh, very early in the computer science career field. If you think about the early 70s, um, no personal computers. Everything was still a mainframe. Everything was still third generation language like COBOL, Fortran, and even those were cutting edge at the time. So this evolution in the software world is based in set theory and mathematics. So the representation of a lot of this stuff is set theory, and I'm not a mathematician. I'm much more of a practitioner. But this notation as we go through here and the theory behind relations and the way they're annotated in the theoretical diagrams, it becomes useful when you start thinking of the way the database engine works in operation, particularly as you start to link attributes from different relations together, different columns from different tables, and you join them. It starts to get pretty complex. The math, figuring out what is going on and how long a query is going to take. It can be useful. There are tools that'll do it for you, but anyway, that's chapter five. We're gonna have to go through um, and I'll focus on the practitioner side, so it won't be so dry, because that's what I'm comfortable with. There aren't a whole lot of people out there in the database world that use, in my experience, that use theoretical um, terminology. They use the language of the database that they're most comfortable with, either Oracle, MySQL, whatever. All right, let's get moving. Um, so yeah, model concepts. We'll talk about constraints and schemas, and again, it doesn't always map one to one with the software, and how kind of how the database handles things. Again, the database engine is just a big piece of software that is looking at the data and looking at operations on that data and making sure everything is handled. So enforcing those constraints is a large part of database software. Um, so a relation, again, we have a lot of terms for the same thing here. A relation starts to look like a table. It's a thing, it's an entity relationship diagram. Um, so there's more on this in six and seven. And there are differences between, like I said, the formal and practical models, the theoretical. Okay. This is the formal relational model. Formal. So it's impractical. Um, and it's like I said, it's a mathematical concept. It's based on set theory. And yeah, EF Cod in 1970. You have to think back at how primitive computing and computers were. So this was fairly prestigious work. And I mean, it had been prototyped somewhat in higher level languages on mainframe computers using traditional files as the actual database. But there was no commercially available software here. Oracle didn't come out for almost another 10 years, and it was another almost 10 years before I started working with that. And it was the early days when I started working with it. So think in context of goodness gracious, 54 years ago. So yeah, informally or practically, a relation looks like a table of values, and it normally contains a set of rows We call those rows a tuple. It's pronounced tuple, not tuple. It's pronounced tuple. Um, and a tuple is an ordered list of values. So think of, a single row coming out of a database with values for each column, or a Python tuple, which is immutable. You can't change it, and it's got a key and a value. The key would be the column name. The value would be the actual value in the database. Um, yeah, so each column has a column header that gives hopefully a meaningful name that gives an indication of the meaning of the data in that column. So this would be the attribute column feature if you are a machine learning engineer. A lot of different names. They all get mixed up in my head, so don't worry too bad if they get mixed up in yours. So here's a relation. It's a table. Okay. It's an entity. The relation name is an entity name. It's the table name. The attributes of that relation or entity are the columns. And each column um, comes from a domain of values. We'll get to that in the next slide or two. Like GPA is going to be the domain of floating point numbers between 0 and 4.0, say. Um, uh, Tuples are the individual rows in the database. It's an ordered list of values. We'll show an example of that here. So that's all it is. It's not that complicated, but the set theory annotation makes it look complicated. And theorists love to complicate things. So go ahead if it makes you happy. Each row has a value or set of values that uniquely identify the row. You can violate that, but it's dangerous. And that's called the key. Normally, um, um, you normally would have the system generate sequential numbers. Um, eh, Artificial key, surrogate key, system generated key to be the primary key of that table. I'll say that probably every week. Um, it's dangerous to use anything real world like um, driver's license number or anything else. It's real world. It's dangerous to use real world information in your database as your actual primary key. You can do it, but when it's a system of record, that's when it's dangerous. Um, I hope the Social Security Administration has some other computer generated number um, as the primary key for me because it can change. Um, they can be uh, entered wrong into systems, and you have to correct it. And if you use it as the primary key, whoop. So anyway, like it's dangerous. So I don't think it's great practice. Okay. Plus, it's real world. You don't want to use someone's social security number in even internally to your employees. You just don't want to do it. So there you go. You always want to mask that. All right. Yeah. The schema of a relation is this set notation. So you got relation, could be person, like we just had student. So student, and then the set of their attributes. R is the relation, and the attributes are A sub one, two, three, four, five. So we've got that example with customers down there, and each attribute, yeah, has a domain or a set of values or a data type, um, a format mask, a lot of different ways to express that constraint on the values that a given attribute may assume. Okay. Tuple, formal definition of a tuple, ordered set of values. And in the annotation. It's in um, tag brackets. Um, so yeah, each value comes from an appropriate domain. Those can repeat, but every column's got to have a data type. So we got a four tuple in customer because there's four values. Um, so one, two, three, and remember this address with the street number and the street and the city and the state and the zip code all crammed in together. Not good practice. We've talked about that before. Same with the phone number, area code, and uh, the LEC code and the last four. Um, that can be a little bit of trouble stored together. You can do it, or you can store it separately because they are different. They're distinct data items. So that's a four tuple. So it's a row in the database. It's uh, a an end-to-a relation, aka a table, is a set of those rows in any given state. We'll talk about the database state. So a domain is yeah just a bound on the values, a boundary. Um, so it could be a what characters it can assume and in what format you can kind of constrain things down like that. Um, a data type and a format and databases date formatting in databases can give you fits. If you try and upload, like I was working with MariaDB not too long ago, uploading client data, and I had to do some massaging to get it into MySQL's preferred date format, which was I think it was YYYMMDD. And what I had was in DD slash MM whatever. So yeah, date formats in a database are a particular domain of values. And it can be bounded by a value as well. Not computers won't store infinity. Okay. And the attribute name designates the role played. And that's why meaningful names are so important. Um, it's used to interpret the meaning. So make meaningful names. When you do your projects for this class, meaningful names. It's going to be more characters. It's going to be more typing. I don't care. It's got to be meaningful names. The domain date may be used to define two attributes, right? Payment date, invoice date, pay date, uh, um, order date, fill date, pick date. I mean, there's a bunch of things that could be dates. So if you just have a column called date, that's trouble. So the relation state, yeah, is a subset of the Cartesian project of um, all the different values that all of the attributes can take. So, it's a lot. Um, yeah, for example, customer name is the, domain of strings of max length 25. Um, and and that's the role that they play. It's just the legal values. This book makes things way more complicated than they need be. Again, because this is all theory. This is all 50-year-old theory that we're going over. Don't let it intimidate you, though. When we get to the actual database fun we're going to have, it's cool. And there's your formal set notation of schema, the relation, the attributes of that relation, um, a specific value that the thing it can assume, um, and the set of tuples, which is just the current state of the database, the value, um, and uh, elements come from a given domain. So this is the expression of all this different database terminology at the theoretical level. You don't write this out when you're working with Oracle or MySQL. You don't generally have to deal with this notation. Okay, so informal terms, table. When in the set theory, when they talk about a relation, it's just a table name. When they talk about attributes um, or uh, features, that's a column. The column header is the name of the column. So yeah, that's what they call the attribute. The column header is just the name. All possible column values is formally known as the domain that those values can come from. A row in the database is a tuple. That tracks pretty well with other programming languages. The definition of a table where you create the columns and the constraints on those columns and the name of the table. That's the schema of the relation. And then when you populate the table with data, we say that's the state of the relation at any given time when it's, you know, at a stable state in between transactions. And that may only be, milliseconds, but that's the state of the relation is the table with the data populated uh, as of that exact time. Um, so yeah, here's our student table. Attributes, tuples. So you've got columns, rows, and a table name. Columns, rows, table name. Um, so uh, the database, if you select all the columns out of a database in SQL, they'll come out in order, but the rows, the tuples, aren't necessarily going to be in order every time, depending on the way the database um, uses space. Um, so the they are definitely ordered when they're self-describing, when you have the column and its value, like a tuple in Python, where you have a key and a value, or XML or JSON. Um, so it's 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 important um, to be overt when you need the order of either the columns or of the rows within the column to be in a certain order. It's important to use the language because you can't count on it in the database. So here's uh, a different order of the tuples. The rows are in different order. Let me look here. Davidson, Benson, Panchel, Kim, Bayer. Bayer, Kim, Davidson, Panchel, Benson. Yeah. Um, you can't count on the data in the database um, being the rows being in a certain order. So you'll always use a sorting clause in your language, whether that's uh, a programming language or SQL. That's all that means. Don't don't read too much into it. Uh, yeah, all values are considered atomic or indivisible, which that's why it's good practice to break up address, for example. Um, and the the values in a column must be, a valid, for that data type or from the domain of that attribute. Um, and they can be null. Um, and there are certain conditions where, null data is considered dirty data, and there are certain conditions where a null is something that you absolutely need to count on being there um, for something that has been unassigned. Because you can't use anything out of the possible domain because it could mess up your processing. Or some database teams decide not to store nulls, and there will be some sort of value within the domain that substitutes for the null value. I've seen that. There you go. Yeah, and the components of a tuple, again, this is set theory notation. So constraints on the data. This is big. This is one of the things that COBOL programmers used to have to uh, code up by hand, constraining the data. So in this model, we've got three types or three main levels of constraints. Inherent uh, is baked into the model. For example, you can't you've got to have an atomic value, right? You can't have a list as one of your columns. You can't have a column whose data type is list, even though it's technically possible for sure. Um, it violates the model, so it's implied, it's implicit, it's inherent. The schema-based and explicit constraints are like where you're doing, a one to n cardinality ratio, and it could be um, a relationship constraint where like state code has to come from the state lookup table. So the two-digit state is constrained. It's a foreign key in the state lookup table. It's constrained to the domain of two-character valid state codes. And a lot of times those are between the US and Canada, I know they don't repeat. Canada does not use for its provinces any code that conflicts with America, so they're semi-compatible. Um, yeah, and then there's application based or semantic constraints. This can be like, you know, multiple conditional constraints that are impossible to model in the relational, but you have to catch the application level. Like, if the person is over 65 and they happened to choose this one product, then we're gonna make them purchase a warranty or whatever. I mean, that those types of constraints aren't modeled. You have to model them more at the functional level or at the application level. All right. Integrity, data integrity. That's a huge constraint that the database watches out for you. This software uh, will alarm either to the end user or to the application developer. It throws errors whenever you try and violate these constraints. And depending on how uh, um, loosely or tightly you want to let the database work, um, you can take the appropriate action. Once it says, "Hey, you're violating your own constraints," hey, you developed this database and you're trying to do something with it that violates the constraints that you set when you created it. So there you go. Three main types of um, constraints: key constraints, where you um, can't have a duplicate. Uh, Entity integrity is inside, like you try to put a string in an integer or something like that. Referential integrity is trying to put a value into a column, like I was saying, state code. You're trying to put a state column that because you have a lookup table for those values. Could be part number, could be something much larger than a two-digit state code, but you're trying to insert a value that does not exist where you're referring to it, Or over on the referring side, you're trying to delete something that will orphan a record. Um, so so the database watches those things for you, manages those constraints. The domain constraint, yeah, that's just making sure that your data type is followed, and it can be null. Useful. So a key constraint, yeah, a super key is just a compound key, where you've got two values, more than one value, more than one attribute. Um, and yeah, a key is technically a super key, but not the other way around. So a way to look at this is like in our practice database. Hopefully you've got that loaded. We're coming up, we're in week 4. Um, like course and section, or a course section. Um, the student grade report. You've got a many to many relationship, um, uh, between courses and students, or and each one of those is a union, and you have to have a compound. You have um, a, a student um unique identifier and a class section unique identifier, and those so you have many course sections and many students. That many to many relationship will be modeled with a super key of the two of those. And then for that unique union of course section and student, you'll have attributes. Um, what grade did they get on test A? What grade did they get on test B? What was their final grade? What was their feedback? All of those sort of things you can store kind of at that super key level. Um, yeah, so you've got this uh, well, it's prospective or possible keys, candidate keys. Let's get to that. There we go. Um, Sometimes a relation can have multiple candidate keys, which is a thing that uniquely identifies you. Um, we probably all have at least three, probably more. Um, I'm uniquely identified by my social security number. I'm uniquely identified by my passport number. I'm uniquely identified by my driver's license number. Those are all candidates for a primary key in a table. But again, it's dangerous. Those are all real world things, but in any given database, it's dangerous because you could have picked it up, could have been dirty data, and you got to change it, and then you're out of luck. Okay. So here we have, yeah, a couple of candidate keys, serial number, uh, uh, engine serial number, the VIN, license at any one point in time. But the license plate can change. That's not a candidate key. Um, you can move that license plate from car to car. You can move the car from state to state and change the license. That's not a candidate key. Anyway, uh, yeah, just the 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 different relations, which is just the tables or the entities in an entity relationship diagram. That's all a relational database schema is the set of relations which would be implemented as tables. So we've got and their attributes. Employee department of locations project works on independent, and uh, your keys are in there. And notice you have a super key or compound key in like department locations and the dependent schema, the dependent relation, sorry. Um, and the database state is just the snapshot of the values that are in there at any given time. um, when it's populated. And you can, what the database engine will do is watch, and it will change the data. It is changing the data. You are not directly reaching in and reading and writing, generally speaking. Um, and the legal operations that change the database in SQL, insert a new row, delete a row out of the database, and modify um, uh, will change the value of a given row in the database for a given column or given columns. And those are usually put in an update table, blah, 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 insert, yeah, yeah, yeah. Okay. So this is, yeah, this is just the database in a given state with its relations and attributes. Uh, yeah, primary key can't repeat. That's all this is saying. Your primary key's got to be unique. And if it's a compound key, no, I'm sorry, this is referential integrity. So this is where you have maybe like a part number inventory table, and then you've got people ordering parts. Think Amazon, an item number and an actual, shopping cart. Um, so you've got the referencing relation and the referenced. So the item number would be referenced. Referencing would be the shopping cart. So you would have a constraint on the referencing relation that it had to exist over in the item table. You can't, or in the item relation. You can't order something that doesn't exist. There you go. Um, Referential integrity. So that's like a primary key, foreign key, right? The primary key in the item inventory table would be a foreign key in the shopping cart table. A foreign key is just a primary key in another table. And we'll have lots of examples of that in your database. And um, there's, theoretical uh, um, notation, and then there's the practical application. Um, yeah, this is just annotation, foreign key constraints. Yeah, just the way they're annotated. So in here, uh, I want to point out a terrible column name, DNO. DNO, come on. That's the department number of an employee. And in our diagram, it shows you that DNO in the employee relation is a foreign key to the department relation or the department table. So DNO would be created with referential integrity, showing that it's a foreign key in um, the department table. And we've got three examples of that. The project has a department number, and the department location, which just has a department number and a location. So a department can be in multiple locations, and that's why you need that. A department can be spread among disparate geographic locations. So those are foreign keys, yeah, and they're using SSN as our employee number. So that's being used as a foreign key um, four times, including this recursive relationship, this parent-child relationship and supervisor SSN, but it's being used in three external tables. Referential integrity, big part of uh, relational database because it's those relations that refer to each other. Uh, Yeah, like I said, semantic constraints. For example, yeah, you can't model um, a constraint that somebody can only work 56 hours per week because anything beyond that violates business rules, say. Um, so you would have to catch that at the application level or in the modern era of databases. Most advanced databases, most commercial grade databases will allow you to constrain the data kind of actively like that. It's not constrained on the model of the data or the schema diagram. It's constrained uh, real time as you go to insert, update, delete. As you go to modify the database has these checks, these little algorithms called triggers, and it will prevent the database from doing something more complex, like adding hours to an employee. As soon as they start to try and track 57 hours, it'll go, whoop, sorry, this, uh, uh, and it's normally just like a little subquery or maybe a little procedural check on the database, um, either trigger or an assertion. I've heard them called triggers. I've worked with triggers, not assertions. Um, so all of these keys, foreign keys, referential are enforced. They're enacted when you create the table in SQL initially, when you create the database. And you guys have got this, even if you're not database people, you've got the create script for your sample database. Hopefully you're taking a look at it and looking at that script and going, oh, I see what where we're going here. Yeah, these insert, modify, update will update the database. The legal SQLs, update tables such and such, delete a column where, um, I'm sorry, uh, delete a row where a certain condition is met. Insert, update, modify. Um, but then you get into the referential integrity, and things can either error or they can propagate to other updates. It can be. Okay, so there's a couple of things the database can do, or you can do as a database developer. You can cancel it. You can, do it above the objection of the database. You can write a trigger that does the right thing. Um, and then there's user specified error correction. Um, these are the possible ways of violating. Again, they are just definitions of the different constraints, domain constraints. So you tried to shove something in there that's the wrong data value. Key constraint, trying to do something where you're creating um, a duplicate row with a duplicate primary key. Referential integrity, again, would be orphaning. Like if you had a dependents in your dependent table in our example, and you deleted an employee, you would first need to delete their dependents. Because if you delete the the employee, their dependents then become orphaned. You'd never be able to find them in a query. Um, so they would sit out there in that table forever, never coming up in a query. So that's one example of referential integrity. And entity integrity. Yeah, you would never insert a row without a value in the primary key. That's why it's good to have system generated primary keys. Keeps you from doing that. Some more violations. More violations. All right. So again, this is sneaking up on something usable with a database. If all of this notation and language in chapter 5 um, makes your eyes water. Don't don't feel too bad. Don't let it dismay you, because the software vendors that actually enact this 50-year-old theoretical um, language have made things a lot more intuitive. I think easier to understand and more practical. And you start getting to something that you can actually touch and feel. These diagrams and whatnot are not software and data that you can actually goof around with. So, but we'll get there very soon. If you haven't already, um, do everything you got to do to download the test database or the sample database that we're using for the project, because I believe we start talking about that next week, and you'll use it a lot this semester, the whole cumulative project. Okay. I'll see everybody in the class discussion. I did a starter thread in the class discussion. I'm seeing, uh, speaking of class discussion, um, you may be under um, the false impression that lecturing each other and providing a few points and then throwing out some basic facts that you say come from some article but don't really, that's really doesn't add any value to the discussion. And if what you're contributing doesn't add value, um, then it's not substantive. We're supposed to have substantive discussion per the syllabus. Okay. The way to do that isn't to, you know, parrot chat GPT to each other. It's to share questions, experience, observation, opinions. Okay. So your initial reply can be somewhat stale and academic. Certainly. It doesn't have to be. It needs to be professional. All posts in class discussion need to be professional. But your replies to fellow students, look at the discussion board. Look at everyone's initial response and the replies made to them. No one has done anything that I could see, and I went through the first half, spot checked the week 3 discussion. No one has replied to a reply. You'll see someone's initial reply or initial response to the discussion, and then you see one, two, three people replying to them with verbiage that um, was likely generated by an AI platform, or it's very stale, very academic. Sometimes I'm seeing some evidence of word spinner because you're using terminology that doesn't exist. And there are article spinning websites that paraphrase things, um, but they use the wrong terms. I mentioned that in at least one feedback. And then I saw something from Course Hero. Someone went out to Course Hero and copied a response to the discussion board. I don't know why someone would post anything to Course Hero, let alone use it in discussion, unless they were just coming to school to get credit, but they didn't want to actually learn anything. I don't know why you're in school if you don't want to learn anything. Um, Certainly better use of your time. But I want to encourage real discussion, actual discussion. I would like to participate in a professional discussion with you as actual professionals, but I need for you to take the discussion board as an opportunity for that sort of interaction, not just something that you spend 30 seconds finding a reply to and sticking it in there. Um, so We'll find out. I'm not gonna I'm not gonna talk about it anymore. I'm just gonna look at things and start giving zeros. And maybe that'll get your attention and maybe it won't. If you don't care about the grade and you don't care about the discussion, then okay, that's the contract that we make as educators. But the current trend is adds no value. It's worthless. So I'll try and encourage you, perhaps because it might be innocent. You may think I I that's appropriate, that's substantive, but it's not. Um, so hopefully we'll have a change going forward because there's like 10 weeks and that's a bunch of points. All right. Hopefully I'll see you in the discussion.